Okay, so in the previous sections, we talked about how to find our zeros, how to solve for our solutions or x-intercepts. Now we're getting into how to draw graphs for these polynomial functions. So again, what's going to happen here is unless we do extensive plotting, we're not going to get the exact shape of the graph, but we can draw a good graph. So we should still be able to get close enough to what the shape of the graph looks like, but we're not going to get the exact shape as though you were using a graphing calculator or one of those to help you out. So how can we go about drawing these graphs for polynomial functions? Of course, we know if you have a degree 0 function, which would actually be something like y equals 4, right? We know it's going to be a horizontal line which crosses the y-axis at number 4. If you have degree 1 as your equation, that is your basic y equals mx plus b format because your x is to the first degree. Again, that's a straight line. It can be line that has a positive slope, line that has a negative slope. Technically, you can also have a vertical line come out of that, right? So 0 and 1 will give us straight lines. Second degree polynomial is our quadratic equation that we saw in the previous chapter and of course the beginning of this chapter, which gives us a parabola. Now what happens when you get into higher degree polynomials, the third degree, fourth degree, fifth degree? Again, how can we go about getting a good graph from some of those? So to be able to draw good graphs, we need to talk about symmetry again. So we'll again talk about, is it an odd function? Is it an even function? For that matter, is it a parabola? Is it bringing its own symmetry? What is the behavior happening at x-intercepts? So is your graph actually going to cross the x-intercept? Or is it just going to do what a parabola does, which will come, touch, and then go back in the direction, or at least go back up or down where it came from? So what kind of behavior are we seeing at x-intercepts? Are they actually crossing or just touching the x-axis at that point? And we also want to talk about the leading coefficient, because the leading coefficient can tell us what the shape of our graph is going to be, which generally means, will both arms of our graph go up? Yes, it will if it is a positive coefficient. Will both arms of our graph go down? That will happen if we have a negative coefficient. But then in some graphs, one arm goes up, the other one goes down, and of course it will just switch depending on what exponent and what sign our leading coefficient has. So with our leading coefficient, we want to see what degree will the x value have. Is it an odd number or an even number on the x? And then of course, is it a positive or a negative sign on the coefficient itself? So those two things will tell us what kind of a shape our graph will have. So those are three things that we need. Then of course, we'll talk about finding our y-intercepts. Do we need to find more points? How do we go about drawing these graphs for these guys? Now, the intermediate value theorem is something very crucial when it comes to drawing graphs. We just really haven't had to talk about it up until now because we were doing all of these simple graphs. So basically what the intermediate value theorem says, that if you have a polynomial function, it takes on every value between any two of its values. So the idea is if I found 2 points on my graph, the intermediate value theorem tells me that from one point to the other, it's going to be a continuous graph. There are going to be no breaks or no jumps that are happening on my graph. So the idea is if I have 2 points that I already used a table or whatever to figure out what these points is, intermediate value theorem tells me that we can be confident there's going to be a point from that one point to the other one, which means there will be a continuity in your graph. It's not going to break apart. If you remember, we had talked about the greatest integer function back in chapter 1. The greatest integer function ended up looking something like this. So as you can imagine, we don't have continuity here because there's a break between these 2 points. There's a break between these 2 points, right? If I just took my pen and tried to follow along with that graph, I would have to lift my pen to make it to the next step, right? I wouldn't be able to do this as one single straight by keeping my pen on the paper itself. I would have to jump to do that. An immediate value theorem tells us you're going to have a continuous graph. You won't have to worry about those jumps happening like it does with the greatest integer function. And this is just the formal definition. So they're basically saying if you have a polynomial function and if there's an interval between a and b values on our x-axis, for which we're saying f of a is not equal to f of b, which means they won't be on a straight line. We're saying there is going to be a value of k between both of these y values where I will have a defined point. I will have a function value for my graph, which basically means you have a continuous graph between those 2 points. Now let's talk about symmetry again. We looked at this extensively before in section 2.3 as it says here. So if you have an even function, you have symmetry with respect to the y-axis, right? If it's an odd function, you have symmetry with respect to the origin. And if it is a second degree polynomial, a quadratic function, it brings its own symmetry, which is the axis of symmetry at x equals negative b over 2a. So these are the 3 types of symmetry we need to remember. Now you can use the test where you plug in a negative x in your function for x and see, do I come back to the original function? If I come back to the original function, I have an even function symmetric about the y-axis. If I put a negative x in for my x and my entire function becomes a negative, basically I'm taking a negative on the entire function, I have an odd function, that means that's symmetric about the origin, and then again, quadratic brings its own symmetry. So what can we say about number 1 here? What kind of symmetry does number 1 have? So we are given negative x to the third minus 4x. So if we want to take and replace our x with negative x, we can see what happens. Do we come back to the original function, or do we come back to a negative of the original function? So that will become negative of negative x to the third minus 4 times negative x. So wherever you see an x, replace it with negative x. We just looked at these properties. Negative base to an odd exponent gives us what? A negative sign or a positive sign? Negative. So we will have a negative left behind from our negative x. So this negative times the negative in the front, negative times negative will become positive.
Same thing for the next one.
Yeah, same thing for the next one. You're multiplying negative 4 with negative x. So again, 2 negatives will become positive. I definitely did not go back to my original function, which I know this is not an even function, but did I get negative of my original function? No? Okay, so what happens if I take my original function and put a negative sign in front of it? So distribute that negative. We will, right? Because negative times negative makes that into a positive x to the third. Negative times negative makes that into a positive 4x, which is what we got. So that means f of negative x is equal to negative f of x. So this is an odd function. What kind of symmetry does odd function have? Yeah, it's symmetric about the origin. Okay, so symmetric about the origin for number 1.
Can you tell it's odd just by looking at it because of the 3 and the 1 exponents?
Yes, exactly. So instead of having to go through this calculation, you can again just look at the exponents. on the original function itself. And this guy is 3. This one, of course, is 1. Both 3 and 1 are odd numbers, which also tells us that it's an odd function, which means, again, it has symmetry about the origin, which I think is the easiest way to do. But just looking at your exam results, we're a little confused about that. So just make sure you are practicing with these to be confident that do I have an even or an odd function. All right, very good. So this is what I was talking about when I said what kind of behavior is our function having at the x-intercepts. So within this same function, you will notice at one of the x-intercepts, my graph is crossing, and at the other x-intercept, my graph will just come and touch the point, but go back, right? It's not crossing the x-axis. So this can happen within the same function. It doesn't have to be one function will do this and the other one will do that. So now how do we decide where it's going to cross and where it only touches? So that comes from looking at the factor of your polynomial. So you'll notice they're not giving this to us as x to the third minus whatever kind of numbers. They've actually factored the function, and then you actually look at what exponent each factor is raised to. So look at here. When I had 2, 0 as my x-intercept, that actually comes from this factor of x minus 2. X minus 2 is raised to an even exponent, right? So when you have your factor raised to an even exponent, your graph touches but does not cross. Now my -1, 0 is coming from this factor here, x plus 1, which is raised to the first power. That's an odd number. So if it's raised, your factor is raised to an odd power, it crosses. Okay, so that's basically what this little test tells us to do. So if your root has a multiplicity of k, because this guy here, 2, 0, has a multiplicity of, actually it's 2, that has a multiplicity of 2, -1 has a multiplicity of 1. When your multiplicity is an even number, your graph touches, does not cross. When your multiplicity is an odd number, your graph will actually cross the x-axis. So that's how the behavior for your x-intercept works. The way I remember this is how your textbook is showing. So think about your basic x squared function. That's a parabola. It will touch, it does not cross. So that's what happens when you have an even exponent on your factors. It touches, does not cross. For the odd number, you can think about x to the third, but you can also think about just the line y equals x. Y equals x also does the same thing, right? Crosses at the origin. So we know when it's odd, it crosses. When it's even, it only touches. So let's put that to the test with number 2 here. So again, you'll notice this is given to us in the factor form. We've got x minus 1 to the third power and x plus 5 to the second power. Take each factor, set it equal to 0. And what will our x-intercepts be coming from these two factors? Yeah, +1, -5. You can start by taking a cube root on both sides of our equation here. Of course, cube and cube root will cancel each other out. And just move that one to the other side. And what multiplicity does 1 have? 3, because that factor was raised to the third power, so that's a multiplicity of 3. So if it's a multiplicity of 3, what behavior do we expect to see at this x-intercept, which will of course be the ordered pair 1, 0. Yeah, when it's an odd number, it will cross. So crosses at 1, 0. And then we said -5 from here. So let's see how that one works out. We've got x plus 5 to the second power. So we need to take a square root. Square root comes with a positive and negative root. 0 doesn't take a sign for either one of those. So we just get x equals -5. And what's the multiplicity for this root? It's going to be 2 because our factor was raised to the second power. Okay. So for this ordered pair, -5, 0, what kind of behavior do we expect when it's a multiplicity of 2? It's an even number, so your graph will touch but does not cross. So it touches but does not cross. Okay. And obviously not all functions will be given to us in the factored form. So for some of them, we may need to factor them ourselves to see what kind of multiplicities our factors will have. Any questions about number 2? Okay, so we've looked at symmetry. We've looked at the behavior at x-intercepts. Now let's talk about the shape of the graph itself. What does the leading coefficient test tell us? So what we're really trying to know is as x is going towards positive infinity or as x is going towards negative infinity, what is our graph doing? Is y also going to positive infinity? Is y going to negative infinity? Or on one side, y is going to positive infinity, but then on the other side, it's going to negative infinity. Like I said, both arms can be going in the same direction. On one arm can be going up, the other one can be going down. A lot of times, you will actually notice these are written in terms of limits. Limits is something that we normally talk about in maybe a calculus course, but we can also talk about limits here. And limits are basically saying as x is going to positive infinity or as x is going to negative infinity, where is your function going? Or where is your y value going? So a lot of times we write it with limits, but then every now and then you'll actually see this notation, which is y with an arrow, which is saying y approaches infinity as x approaches infinity. Y approaches negative infinity as x approaches negative infinity. You will also notice your textbook gives you a little graphical method to see, do I have a positive or a negative coefficient? Do I have an odd or an even exponent on my coefficient? So there's 3 different ways for you guys to try and see which method works the best for you to try and remember what kind of leading coefficient test we are going to have. So it comes down to, if this is my polynomial, I'm only looking at my leading coefficient. A sub n in this notation means the constant number, right? Which is your coefficient in front of the x value. The x to the n is talking about what is the highest degree on the x value. So the n that we're talking about here or in here is talking about this number here. Is it an odd number or an even number? The a sub n, we're talking about the coefficient in front of that x variable, and we're talking in terms of, is that a positive number or a negative? So there's 2 things we need to know. Is my number going to be positive or negative? And the second one is my exponent odd or even number? So if it is an odd number with a positive coefficient, then that actually means one arm is going up, the other arm is going down. If it is an odd exponent with a negative coefficient, it's still the same thing. One arm is going up, one arm is going down, but they change directions. Okay? Even with a positive, so if it's an even exponent with a positive coefficient, that's basically your x squared. Both arms are going up. If it is an even number with a negative, You can think of that as being your negative x squared reflection, right? Both arms are going down. So these two, we've actually talked about it in terms of parabolas. The odd ones, not so much, but you can always think of your odd ones. Let me see if I can find that graph right here. So if it's a even exponent with a positive coefficient, my arm goes up. If I just put a negative in front of that x squared, I'm going to have a reflection, which means both arms go down. If it's an odd exponent with a positive coefficient, then as x is going to positive infinity, y is also going to positive infinity. So they're both going in positive direction, right? If x is going to negative infinity, y is also going to negative infinity. So that is my odd exponent with a positive coefficient. Now, if I slap a negative sign in front of this x to the third, that's a reflection, right? Which means this arm will go down and this arm will go up. That's how the direction is going to change. And instead of x to the third, you can also think of this as being y equals x as your graph. It works either way. So to remember your leading coefficient test, if it is an even exponent with a positive coefficient, both your arms are going to go up. Okay, think about your y equals x squared function in this case. And remember, that's your basic parabola with both arms going up. When it's an even exponent with a negative coefficient, both arms are going down. So think about y equals negative x squared. This is a parabola that's opening downwards. So this will be true for a fourth degree polynomial with a positive or a negative exponent. Coefficient. This will be true for x to the 6th, x to the 10th, anything that's an even exponent. So in that same sense, if we have an odd exponent with a positive leading coefficient, so for that, you can think of the cube function, or you can just think of y equals x, which is a line with a positive slope going up. So in this case, one arm is actually going up and the other arm is going down. And odd exponent with a negative coefficient, think about y equals negative x. This is now a line with a negative slope going down. So that means one arm is going up, the other arm is going down. Of course, these guys have now changed directions because of the reflection. So use whatever technique helps you out to remember the leading coefficient. I've given you a table. This limit definition is given to you in your textbook. And then, of course, the graph is also given to you in your textbook. So here we're talking about, do I have positive coefficients? And then is it an odd or an even exponent? So that's where these graphs are coming from. Is it a negative leading coefficient? And again, in terms of odd or even, where they come from. All right, so look at the definitions, look at the tests, whatever you want to use. You can try and use this guy here. What do we say about example 3? What is the shape of our graph going to be like? So do we have even positive, even negative, odd positive, or odd negative on number 3? Odd negative? Trey, is that what you said?
Yes.
Okay, let's see. Is there any doubt it's going to be anything else? No, because my third power is an odd number and I have a negative sign, right? So what kind of behavior do we expect when we have an odd exponent and a negative leading coefficient. So what's your conclusion on that? What kind of shape do we have? As x goes to positive infinity, where is the y going? Y goes to negative infinity?
Yes.
Okay, quick check here. We're talking about odd and negative, right? So this is my shape of the graph, which means if x is going to positive, y is going down, which means it's going to negative. So obviously on this side, I'm going towards negative infinity. So as x is going to negative infinity, y is of course going up to positive infinity. And you can actually write that down for all the other descriptions also. So yeah, y will be going down to negative infinity. And then for the other one, as x goes to negative, y is going to positive. This is one way of writing it. You will see both the limit and this notation of how our values approach. So with limits, we write it like this. You have limit. Underneath that, we write x going towards positive infinity. For our function, f of x, so when x is going to positive, my y value is going to negative infinity, right? So this will equal negative infinity. So for the second part of our shape, we will write limit as x goes to negative infinity. Our function f of x is going to positive infinity. So one arm will be going down, the other arm will be going up.
Are we gonna do the limits part for the test?
Okay. So you should be comfortable writing in both formats, and you will actually see homework problems on that, so you should get a little more practice when you do this with the homework. Symmetry, behavior at x-intercepts, and the shape of the graph based on the leading coefficient test, right? Those are the three tests we will be doing. Then, like I said, we'll need more points since those three things will not give us all the information we need. So let's talk about how can we sketch a good graph. Start by checking your symmetry. Then find all the zeros. Now remember, your zeros are finding your x-intercepts here. So find the x-intercepts, then talk about what behavior is happening. Are they touching, or do they actually cross the x-axis at these intercepts? Then they're talking about the behavior as x goes to positive or negative infinity. This one here, number 4, is your leading coefficient test, the example that we just did. Calculate several other ordered pairs. Make sure one of them is a y-intercept. And then hopefully we should be able to get enough points that we can draw a smooth curve and draw our graph. So let's start here with number 4. You've got your grid on the other end. So let's talk about symmetry first. What kind of symmetry does this function have? Okay, and how do we know that? Yeah, because both my exponents on the x values are even numbers. So I've got x to the 4th and I've got x squared. Since both my exponents are even numbers, this is an even function, and even functions are symmetric about the y-axis. All right, so we've talked about symmetry. Now let's find our x-intercepts, or our zeros. To To find our x-intercepts, remember, we always make the y value 0. So let me see what x-intercepts you guys come up with. Where are you going to start by trying to find the zeros for this function? You've got to do something, right? To be able to solve this, to set it equal to 0.
Factor out x squared.
Yeah, you want to start by factoring out an x squared. So we get an x squared outside. How many am I left with from x to the 4th? Yeah, I'll be left with 2. Minus 4, we already took that x squared outside. Okay, very good. So we start by factoring. Then what do we do? Sorry?
Can you factor x squared minus
You can factor that further down, yes. So what can we factor that into x squared minus 4?
x minus 10x plus 4. Plus 2.
Yeah. So you can actually factor this down into x minus 2, x plus 2. This is actually of the format perfect squares, difference of perfect squares, because you can write 4 as 2 to the 2nd power. So that's x plus 2, x minus 2, which is coming from x squared minus 4. And you can always multiply that to confirm that. Okay, so now we've completely factored this. Now what can we do?
Take each individual one and put it equal to 0.
Yes, take each individual factor and set it equal to 0. All right, so we should get 3 different x-intercepts out of this, and then we should be able to talk about the behavior at each one of those intercepts. So x squared equals 0 will give us what? X equals 0, right? Because your square and square root cancel out, you get x equals 0, which is of course the ordered pair 0, 0. Or what will the second one give us?
2.
Positive 2. Very good. Which is of course the ordered pair 2, 0. And this last one? Negative 2. Very nice. Which is again the ordered pair negative 2, 0. Now let's talk about the behavior. So remember, this is based on what multiplicity they have, or what the factor was raised to, an odd exponent or an even exponent. So for the x equals 0, with the x-intercept being at 0, 0, will it touch or cross? And we know that because, yeah, this is raised to the 2nd power, which means we have a multiplicity of 2, and since that's an even number, at this point our graph touches but does not cross, right? At x equals 2, what kind of multiplicity does that have? 1. So that means our graph is crossing at 2, 0. All right, very good. And at negative 2. Same thing, multiplicity of 1. So again, it's going to cross, but, it crosses. So at 2 and negative 2 is going to cross, at 0, 0 is going to touch, but not cross. All right, so that's your behavior at the x-intercepts. Now, what does the leading coefficient tell us? X to the 4th is what our leading coefficient is. So is it odd, even, positive, negative? Positive and x to the fourth.
Oh, and negative. Yeah.
No, just look at the first term. First term of your function, which is x to the fourth.
Positive.
Positive and odd or even?
Even.
Yeah, so it's positive and even. So remember, positive and even is the same as our y equals x squared, which means both arms are going up, right? So that's going to be as x goes to positive infinity, y also goes to positive infinity. As x goes to negative infinity, y will actually still go up to positive infinity. In limits, as x goes to positive infinity, our function goes to positive infinity. As x goes to negative infinity, our function will still go up to positive infinity. So both arms are going to go up. Okay, so we've done the main three tests that we needed to do. We've talked about symmetry, we've talked about the behavior at x-intercepts, and we've talked about the leading coefficient test, what our arms are doing. When we come back next time, we'll find more points. So we'll start by finding our y-intercept, maybe find a few more points and see what kind of shape this graph will have. All right, guys, have a wonderful evening. I will see you on Wednesday. Bless you. And looks like we're matching more than halfway through with this handout. So we may be looking at Monday as a possible test day for chapter 3.